each other, essentially creating a meshed communication network. So with this technique, we're going to be able to reduce some of the issues that are problematic in indoor communications. So some of the factors that motivated us to choose this particular project involve having field trips being a really important and valuable experience to children's education, but that doesn't go without risks and concerns. So our technology is going to take safety into a top priority for these children. It's not easy to keep an eye on kids at all times, especially in dense populations like New York City museums or public transportation. So you want to have an eye on all of them, and this technology will help reduce some of that, reduce some of those concerns. And current technology really relies on carrier services such as cell phones, Wi-Fi reliant technologies, GPS tracking devices. We're making our technology completely standalone so that we don't have to run into faults or places where there's not enough communication. And also there's a lot of parallel applications that we can tailor this project to. So for example, we can apply this technology to cruise ships and properly address overboard scenarios, because it's actually a thing. Since 2000, there have been 85 known cases of overboard situations. Another implementation would be recreational hiking, for example, where cellular service or Wi-Fi is quite limited. So in order to meet our goals, we need to meet a criteria of system requirements. So I'm going to pass it on to my colleague Jorge Montoya to go over some of the system requirements.
All right, so these are the requirements for our systems. We split it up into both consumer and technical requirements. So on the consumer side, you typically want a low cost. You want a low false positive rate, so consumers generally don't want an inaccurate system. As we discussed before, we want it to be standalone, and we want it to be portable and lightweight, and to have sustainable battery life. So now for technical requirements, the first requirement is we want low transmission power. This is to make it possible to have that sustainable battery life and to comply with the FCC. We want low processing time, so we want our system to be both accurate and quick. Because we're working indoors and because we have multiple devices, we have to account for the multi-axis and multi-path effects to our system, and we want to have low spectral footprint. Now I'll pass it over to Steve Miller to get more into the specifics of our system.
Originally, we were trying to implement a time-of-flight calculation to measure the distance between 2 points, primarily our base station and wristbands. The reason why we chose this is simple in theory. However, we found that it was pretty difficult to implement in a real-life scenario. The reason why we chose it is because there's a direct correlation between distance and time given by this equation. Generally speaking, the distance can be measured by the time of flight divided by the speed of the wave. It's pretty accurate for indoor applications. However, it turned out that it can be pretty expensive and difficult to implement. The main issue would be the synchronization of the wristband and of all the wristbands and base station's clock. We'd have to synchronize it down to 1 nanosecond of disparity, and as you can see here, large disparity creates a larger error, and this just was pretty detrimental to the project, so we had to switch to a new method that Chris Coloso will now discuss.
All right, so we're going to create a mesh network between multiple wristbands and our base station using RSSI. We're going to design the system to utilize line-of-sight communications, which RSSI is totally capable of. Each wristband, if there's no direct line of sight to the base station, will hop to another wristband within the radius. It will forward its distance calculated, the hop incremented if it hopped beforehand or if it's hopping now at the base station. It'll calculate the watchability factor, which is 1 over the distance cubed times the number of hops. We determine the distance based on the path loss between either the wristband to wristband or wristband to the base station. And we'll pass it on to CMO to describe some scenarios.
Yeah, so we set up a few different scenarios in a museum setting, which is kind of a stereotypical field trip setting. We have 3 groups of children. One, we have a group over here of children that are in line of sight and relatively close to the base station. 2, we have children that are somewhat far but still in semi-visible area. And 3rd, we have the children that are both far away and not in line of sight of the base station. So we're going to take this first scenario over here, where we have a direct line of sight between the base station and a hop distance of 3 meters. So this is a simplified version of that communication path. And we have 3 watchability thresholds. We have a green, yellow, and red alert stage. This first case will be within the green stage. So sample calculation would be 1 over the distance, which is 3 meters cubed, times 1 hop would leave us with a watchability factor of 1 over 9, which is well within our green safe location. A second scenario would be a 2-hop method, where there is no direct line of sight between the base station and child. So we have a total hop distance of 3 meters and 13 meters, which leaves us with 16 meters. This again is a simplified version with 3 meters and 13 meter hop, and a direct line of sight will be impeded by a wall. The watchability factor, again, is calculated by the distance cubed times the number of hops, which leaves us 1 over 8,000, which is below our green threshold, but not enough for our red threshold, so we're left with a yellow cautionary statement. Last scenario, we have a 3-hop system where there is no direct line of sight between the base station and children. We have the first 2 hops, which add up to 16, and another 4-meter hop, which adds up to a 20-meter total distance. Again, simplified model. We have the distance cubed times the number of hops, which takes us well outside of our red range. This system really takes into account more than just the distance, but also the visibility of the children. I'm going to let, as far as our simulation and our hardware implementation, we have to send out signals from both the wristband and the base station. On the wristband side, we have it chunked into 3 different areas. We have the wristband's unique ID, so we can identify which signal we're receiving. We have a total distance calculation that's being cascaded continuously, and we have a hop count that's also being cascaded continuously on each hop. From the base station side, we have a unique base ID, so each wristband can identify whether the base station is trying to reach out. We have an alert status and connection status that we're going to use within certain algorithms on the wristband side. And if we have to alert a certain wristband that they're out of range, we have to know which one that we're talking to. As far as certain standards, we will be using Zigbee and IEEE 802.15.4 to deal with our signal forwarding. Unfortunately, it needs to be interrupted to perform our main functionality, to increment the distance and increment the hop count. We will be addressing certain multipath effects by using DSSS, CSMA, and exponential backoff. This again is more important in indoor environments where multipath and multi-access are issues. Just a little more specific, the physical and MAC layer is addressed within 802.15.4, and this mostly deals with signal interference scheduling. So we know when we're transmitting and when we're receiving, so we don't interfere with each other. And I'm going to let Chris Delosa take over on a certain simulation that we did for each case.
So this is a simulated model we developed. So this is case 1 that Stephen Miller mentioned earlier and explained. So we have wristband 0 over there communicating directly to the base station. The base station calculates total distance of 3, total number of hops is 1, and it calculates the watchability factor to be under the green threshold to give us a green condition. Case 2, you have 2 wristbands talk to each other. You have wristband 0 talking to wristband 1. Wristband 1 calculates the distance to be 3, total number of hops to be 1, and it sends that signal out to the base station for the total distance to be 16, total number of hops is 2, and the watchability factor to be in between the green and red thresholds to give us a yellow condition. Here we have case 3 where we have 3 wristbands. We have watchband 0 sending the signal out to watchband 2. Wristband 2, calculating distance to be 3, total number of hops to be 1. That will be sent out to wristband 1, calculating distance to be total 16 meters, and total number of hops to be 2. And then finally to the base station, calculate the total distance to be 20, total number of hops to be 3, and the watchability factor to be just above our red threshold to give us a red condition. So I'm going to pass it off to Jorge Antoine to explain the accomplished task.
So now we're going to go through the general process of our accomplishments throughout the semester. So we began by defining the project outcome or goal was to create this monitoring system for children to be used indoors. And we continued, we looked into time of flight calculations. We did calculations, we did simulation, but we ended up discovering that this was not feasible due to limitations on our resources that we had. So we had to turn over into RSSI, and we were able to implement the watchability factor that we created, and we were able to, as you saw previously, show the simulations. So the point that we're at now is that we're translating the simulation into the physical components that we will plan to use in the future. And now I'll translate on to Jeffrey Chung for future plans.
So these are our future plans. Immediately during winter break, we want to start an implementation with Arduinos and XPs.
and we want to establish reliability. That means after testing, we understand how the hopping is going to work in indoor environments and how the RSSI threshold will change with attenuation through different types of materials. By January, we hope to finalize that Arduino prototype and finish all that testing. In February, because this is a product that we hope to eventually become a consumer end product, we're not going to stick Arduinos and XPs on children's wrists. So we're going to design our own custom radio circuitry and enclosure, and we're going to start ordering the components for the breadboard. By March, we're going to breadboard components, establish functionality, test the hardware prototype, and this testing will be similar to the testing we implement with Arduino. We're also going to start ordering the custom PCBs, and by April we're going to have the final PCB, test the final project, and present in May. So we organize the project risk into 3 main categories. Technically, we have environment. So one of the reasons we did switch to RSSI with hopping is because of the inherent issues that come with transmitting signals in environment. The second one is requirements. 2 of our main requirements that may pose a risk is reduction in size and meeting our budget. Third is complexity. Using all these IEEE standards and communications indoors provides its own complexity. And PCB design. PCB design itself isn't exactly easy and has its own standards, and in doing that for RF applications presents even more complexity. Organizational, the only possible risk we see right now is funding. Jorge Montoya is going to discuss the budget in a little bit, and that budget is contingent on everything going to plan. Project management, strict scheduling, and time limitations. As of right now, for our testing procedures, we have maybe a month for Arduino testing, and then breadboarding, and then PCB testing. Compared to a real-world application, I believe that's a really short time, and that's probably one of our biggest issues with project management, and then vendor contact. We'll be moving from Arduino to breadboarding to PCB design relatively quickly. We're going to have to keep in constant contact with vendors and make sure we can get our parts on time. As far as the testing plan procedure, we really have two main things we want to do. One is testing in different indoor environments. This means get an accurate representation of our signal strength map, and therefore model our RSSI threshold based on that. And then we also want different scenarios where hopping is occurring in different numbers. Secondly, we want to stress test our base station. We want to understand the processing, what the processing capabilities are, and therefore how we can modify our algorithm to meet for that. And then Jorge Montoya is going to discuss the budget.
So this is a general outline of our budget. We divided it both into prototype and into the actual implementation or final implementation. So we're going to need 4 Arduino Zeros, which will be supplied by Manhattan College, and 4 XP transceivers. So our total cost for the prototype should be around $70. And for the final implementation of the system, we're going to order the custom PCBs. Our total for the wristband should be around $38, and total for the base station should be around $44. This makes our grand total $226 when you take into account the fact that we're going to be using 3 wristbands and 1 base station for this.
Just one note about the budget, it's still in a pretty preliminary stage because such things as battery requirement is deterministic on our power circuit design and how much power is being drawn. So we did not factor those into the budget at the moment because we are completely unsure about how much power we'll be drawing because that's all dependent on the circuit design that comes in a later stage.
So in summarization of some of the key concepts we brought up, we want to create a reliable device that will track large groups of people in vulnerable areas. So our mesh communication network will essentially give us an easier way of maintaining communication between the devices in indoor environments, which poses a challenge. We're going to utilize standalone communication because we don't want to be reliant on other technology that has a possibility of failure. And we're going to implement this simulation, this design into a physical hardware proof of concept, and hopefully into a fully demo product. So with that, we open the floor to questions, concerns, and comments, preferably kind ones.
2 comments and then a question. The comments are, thank you for, one is just a statement. Thank you for the simplified milestone chart as opposed to the Gantt. Number 2 is, I think, hitting the major risk as budget cut, and you mentioned it several times, is also reality. Just from a technical side, the question of this usage case of children in clusters, I guess that's more natural, phenomenon here as opposed to, strung out. How does that affect the performance of this?
That kind of plays into, if you want to go back to the slide with the walkability factor, that kind of plays back into our figure of merit. Our hop count is a general outline of how far the kids are, how the line of sight between the kids and each other and other kids. So that plays more. One more slide back. Right down here, we wanted to factor the distance. Why we cubed the distance was we wanted to have the distance between wristbands as a more influential factor than the number of hops. So if I'm hopping from here to there to outside the room, the distance between me and the final hop would be more of a factor than the number of times it hops.
Okay, thank you.
I have a question. Regarding the time of flight that we applied at the beginning, and you disregard the technique, correct?
Yes.
What was the rise time of the start signal? What was the rise time of the stop signal?
That was the whole issue why we had to discard it, because it was very difficult, one, to model.
I was modeling.
Yeah, it was modeling. This is why we had to discard this technique.
What signal you use? What was signal you use?
We were trying to use a spread spectrum signal to lower the response time.
You find problem with the modeling. Typically, modeling, to find the rise time, you find the approximation of the signal is Gaussian. You consider the signal is Gaussian, this is the way to do the modeling. So you are restrained by modeling to do, not actual measurements.
A little bit of both, because we were limited by hardware synchronization and modeling the processing time as well.
Yeah, but to do hardware synchronization, you have to have some knowledge of the signal, the rise time of the signals, the transmitted and the stop signal, If you don't know, what was the distance involved?
We were looking anywhere between 1 and 50 meters.
1 and 50 meters.
So that was part of the problem too with close proximity. It was even more difficult to obtain. And on top of it too, the cost of the actual clock that gets down to that half-hour
let me tell you, interesting project. If you need some other funding, you let me know. Okay.
Okay, unfortunately, we're going to have to move on, but thank you very much, gentlemen.